Okay. So as I was saying in the last video, thus far, there's no reliable method that exists for making short-range earthquake predictions. And with that, I want to show you this short SciShow episode, which I think is great. If you haven't seen SciShow, it's pretty cool little site, so I recommend it.
On April 6, 2009, an earthquake struck near the Italian city of L'Aquila, killing nearly 300 people. It was a terrible disaster, and you've probably heard of it because 6 Italian scientists and 1 government employee were later tried and convicted on criminal manslaughter charges for providing inaccurate, incomplete, and contradicting information about the earthquake danger. They were sentenced to 6 years in jail, basically for failing to predict an earthquake. This has riled up a lot of folks in the science world, and with good reason, because while we know a lot more than ever about earthquakes, there is still no reliable way to predict them. Now, can we forecast where earthquakes are likely to occur over a long period of time? Yes, of course we can. For example, scientists know that there have been 20 major earthquakes of magnitude 9 or higher in the Cascadia region between Vancouver and Central California over the past 10,000 years. The last one took place in 1700. There will be another in the future sometime. But can seismologists predict the time, epicenter, location, and magnitude of the next Cascadia earthquake? They cannot. There are lots of reasons for this, but it's mainly because it's so hard to study tectonic plates, the giant slabs of the Earth's crust that are always moving around, since they're usually at least 100 kilometers thick. So while scientists believe that quakes start when 2 or more plates meet, the process that occurs before they start is subtle and almost impossible to observe.
So you saw from the video of the SciShow, basically, predicting the earthquakes is no easy task, definitely not short-term predictions, and unfortunately, those 6 scientists and 1 government worker were sentenced due to their, if anything, malfunction of predicting earthquakes, which could not happen in the first. So in contrast with short-term predictions, which aim to predict earthquake within a time frame of hours or days, long-range forecasts are estimates of how likely it is for an earthquake of a certain magnitude to occur on a time scale of, say, 30 to 100 years or even more. So long-range forecasts typically give statistical probabilities of the expected intensity of ground motion for a given area over some time frame. So the data from these help with developing guides for building codes for buildings, for example, or also building codes for dams and roadways in an area, so that they may withstand the future and likely shaking events in the area. So many long-range forecast strategies are based on evidence that many large faults break in some sort of cyclical manner. So the cyclical manner means that there will be a displacement at roughly similar intervals. So, for example, if there is an earthquake tomorrow in Boise of magnitude 6.5, and we have typically seen that there is one of that same magnitude every 100 to 120 years, then we should expect the next 6.5 magnitude earthquake to happen in about 100 or 105 or in 10 years. So the rate at which the strain builds up can be calculated by the motion from the plates in question at the site where the long-range forecasting is being done. So that is not a very hard task, as we saw in chapter 2. This plate motion can be seen, and so the strain can be calculated. And based on some past knowledge of past events, we can also make maps of the areas that have a high and lower possibility for earthquake occurrence in a specified range of time, like the one that you're seeing here on the top right. So one of them has, or I should say, some areas like California and like Alaska have very high hazard in terms of earthquakes over a specific time range, which I'm not sure what it is for this map. And some of them have a very low hazard, like Minnesota, for example. So one method of study is locating seismic gaps, for example. So seismic gaps are areas in a seismic zone where no earthquake has occurred in the last 100 or several hundreds of years. So these areas, which they believe are accumulating strain that will later be released during a future earthquake, are shown in the figure on the left, for example. So this is a seismic gap read in this section. So in the megathrust, the Sunda megathrust, which happens when with the Indian plate or colliding against the Eurasian plate here in Sumatra in Indonesia, we have seen a set of earthquakes occur throughout the megathrust. However, this specific area has seen no earthquake in the last 100 or several hundreds of years. And so it's a seismic gap where scientists believe it is accumulating strain for it to later be released as energy in the next future earthquake. Another method of study is paleoseismology, and this is the study of ancient shaking events. So much of the work done here is through digging trenches in areas of suspected paleoseismicity. By digging these trenches, the different sedimentary rock units and their nature, their shape and organization will provide clues as to whether or not they experience some sort of faulting. If faulting is found to have occurred in that area, then sometimes, for example, carbon dating can be done in any remaining organic matter that, for example, got buried within the unit. And so there can be some sort of quantitative estimate of how old that fault is and hence how long ago that earthquake occurred. So this is a hazard map done for California state. As you can see, much of the state is, prone to earthquake activity, especially the southern San Andreas fault zone for the most part. So you're seeing that this area is for sure going to have an earthquake of 6.7 magnitude in the next 30 years. So overall, these kind of maps are incredibly useful in order to detect or to have some sort of prediction, at least in the building codes, of how the area should be developed and should be prepared for such events. Alright, so based on all that we've covered so far, we've seen that seismic waves used in locating and on measuring the earthquakes is incredibly useful. Knowing how the seismic waves are going to behave has also given us a better understanding of the nature of the Earth's interior, for example. So, all geologists would love to just go ahead and study the Earth's interior, be able to basically slice up the Earth and see what's inside of it. See it chemically, physically, see it geologically. But unfortunately, we can't do that, even though we have tried. So we have tried drilling at relatively large depths. The deepest that a drilling rig has ever penetrated is only about 12.3 kilometers or about 8 miles in depth. And this happened in 1992. So that depth of 12.3 kilometers is only about 1/500th of the way to the Earth's center, so not very deep. And although this was overall a pretty great accomplishment, and this is due because, again, the pressures and the temperatures keep increasing as you get deeper within the Earth. So by the time that they reach the deeper parts of their drilling, the temperatures were of 300, 350 degrees Celsius, so they could no longer go any further. It only still made it only about a third of the way into the Earth's crust. So we're not able to study much deeper than that based on at least physical methods. So by this drilling, we did find some rocks that were 2.7 billion years in age, which is pretty cool. So overall, a pretty good attempt. But because we cannot use this more kind of intuitive methods, we use other tools to help us see what is at depth. So in earthquakes that reach magnitudes of 5.5 or so, the seismic waves can travel throughout the Earth's interior, and they can be recorded in a seismogram in the other side of the world. So the body waves, which again are P and S waves from these large earthquakes, can be used to basically see into the planet. In much the same way in which doctors use, for example, ultrasound waves to generate sonograms through which we can look at babies. So there are about 3,000 earthquakes of at least that magnitude, 5.5, that occur every year in the world, which overall brings a lot of data for us to go ahead and study. Okay. So one thing to recall is that P waves are going to be faster to travel, and they're going to be able to travel through solid, liquid, or gas, and that S waves can only travel through solids and are also slower. So understanding seismic waves is pretty key to understand the Earth's interior overall. Seismic waves will travel again faster through denser material, through material that is consolidated and has been compacted. Okay? So they will travel faster through consolidated, denser material. And they're going to travel slower through unconsolidated material. So due to this is why they appear as curved lines in the image on the slide, for example. So you're seeing that they appear kind of as curves, and that has to do with the differences in density of the rocks as you get deeper within the earth. It's going to have some change in the rate at which those waves are traveling. So typically there's going to be some increase in speed as you increase in depth. Overall, seismic rocks may also get, seismic waves may also get reflected. They can get refracted or diffracted off different layers due to the density differences between those layers in the Earth's interior. So when you have reflection of the waves, like in this case, you have them basically bouncing off a specific boundary density difference layer back to the surface, in which a seismogram can record the arrival of that wave. You can also have the waves be refracted like you have over here. So this specific wave has traveled through the outer core, which is liquid, so it must be a P wave, but it got refracted. So the rate at which it was traveling here in the mantle is different than the rate at which it's traveling through the outer core. And then it gets refracted again once it goes back into the mantle part on the other side of the world. And some of the waves can also get diffracted, in which case they won't travel through a specific layer, but they will kind of travel on the outside of it and then get re-radiated like you're seeing over here.